Good evening. Today I'm going to show you how to count the number of ways to distribute n distinct items into k identical boxes. Okay? So the number of ways to distribute n distinct objects into identical or indistinguishable boxes. Okay? Now I'll start with small values of n and k. Now let me start with this example. Suppose we have three fruits. Okay? Let's say an apple, a banana, let me call it B, and an orange. Let me notify off. Okay? These are distinct objects. They have different measures. And I want to count the number of ways I can put them into, let's say, two identical boxes. Identical boxes. Say this box and that box. Okay? Well, they don't look like a box. That box and that box. Okay. One way is to put the apple here, the banana there, and the orange there. Now we do have these two boxes. One is banana and orange, one is an apple. The second option would be the banana would be there. I can have an apple and an orange there. The third option is I can put all of them in one, banana and orange, and leave the second one empty. And the fourth could be I can put, let's say, the orange in one, and the banana and the apple in the other one. Since the boxes are identical, indistinguishable, it doesn't matter, if I have the banana and the orange here and the apple there, and so on. They just contribute one to the whole total count of the distribution. Okay? So you can say that there are 4 ways to do the job. 4 ways to do the job. But you see, problem is for big n's and k's, it's very difficult to draw and count or to touch them by hand and count the distributions. That's why we need to learn the art of counting. Okay? Now, the idea that will lead us to that will be, okay, now we have 3 distinct items. I'm going to think about 2 numbers, because we have 2 containers, 2 numbers that will add up to 3. Well, everybody knows that 3 plus 0 is 3. This could mean, I can use this to mean, or to think of, putting 3 of the fruits in one box and leave the second one empty, zeros. So this is like the distribution, all the fruits here, orange, and that one is empty. Okay, leaving that one empty. And the other possibility is adding 2 and 1. 2 plus 1 is 3, or 1 plus 2 is 3. It doesn't matter, because whether I write it as 1 plus 2 or 2 plus 1, because it will give us the same scenario of the boxes, because the boxes are identical. One will have 2 fruits and the other will be empty. So 2 there and 1 there. But in the second one, since we have 3 fruits, okay, 3 objects, distinct objects, I need to count the number of different ways to pick 2 out of 3 distinct objects. You see, it can be the apple and the banana, it can be the apple and the orange, or it can be the banana and the orange. You see, there are 3 different ways to do that job, to select the 2 fruits out of the 3. Therefore, you can say that here 3 is equal to 2 plus 1, but there are 3 ways to do this. To put 2 fruits in one box and 1 in the other. Now, here we have 3 ways to do the job. For the second one, and for the first one, there is only 1 way to pick 3 items out of 3. There is no other option. Therefore, 3 plus 1 will give me 4. You see, I have already counted them because the numbers n and k were small, and the result was 4. And I obtained the same result through another approach. And this is the approach we're going to use in order to solve with distribution problems of the same nature with larger n and k. So, can I add one more example? I think it's good to add one more example. Example 2. Okay? Suppose I want to count the number of ways to distribute. Let's say 5 distinct balls, items, into 3 identical boxes. Okay? I want to count the number of ways I can distribute 5 distinguishable items into 3 indistinguishable boxes. Identical boxes. Well, that's how we did it here. Now, I have to look for 3 numbers, and I have 3 containers, 3 numbers, which add up to 5. So, obviously, 5 plus 0 is 1. Okay? And there is 1. There is only one way. There is only one way to pick 5 out of 5 distinct objects. Okay? So there is only one way to do that. That kind of arrangement. And the second one is that 5 can be obtained as a sum of 4, 1, and 0. This means 4 objects in one box, 1 in the other, and so on. Then leave the third empty. So I can say that there are 5 to 4 ways to do this. Okay, 5 choose 4 is a 5 combination 4, which is equal to 5. Now, let's see the third one. There's another way, obviously there are other ways to do so. It could also be 3 plus 2 plus 0. It means putting 3 items in one box, 2 items, or the remaining in the other. So you see, there are 5 to 3 ways or 10 ways to do this. Because there are 5 to 3 ways to pick 3 out of 5. And I'll be left with 2 items, and that will go to one of the boxes. Therefore, there is only one way to do the remaining. So we have 10 ways to do this job. And the third one, this is the fourth one, 5 can also be given as 3 as a sum of 3 plus 1 plus 1. Now each box has some object. 2 of the boxes have 1 and 1 box has 3. So here there are, let's say, 5 choose 3 ways or 10 ways to do the job. So we have 10 ways to do. And one last way to form 5 as a sum of 3 numbers is 3, I can say 2 plus 2 plus 1. That means 2 of the 5 in one box. Then I'll be left with 3. Then I have to choose 2 out of the 3. But since the boxes are identical, I have to divide the product by 2, so that we can have unique avenues or unique ways of distributions, unique distributions. So there are here. Okay, first I pick 5, 2 out of the 5. Okay, 10 ways, but I'll be left with 3, and I have to choose 2. So times, because this is the product rule, 5 choose 2, 3 times 3 choose 2, and I have to divide this by 2, because the two boxes are interchangeable, so I don't have to count them twice, and this is going to give me 15 different ways. Now, I think there is no other way of forming 5 out of or as a sum of 3 non-negative integers. Okay? Therefore, there are how many ways? Well, here I have 1 way, the first one way. Here I have 5, 10. So we have 1 plus 5 plus 10 plus, the other one is 10 too. 10 plus 15, that's 25, 35, 35 plus 6 is 41 ways. Thank you for listening.